Math 7, Unit 7, Lesson 7, Part 2, Probability of Compound Events. Now we've done a lot of work on compound events already and even learned how to calculate their probabilities, but we're going to learn some shortcuts and additional understanding, gain some additional understanding through this lesson. Okay, first, from the notes, the vocabulary. Compound events, it's a group of outcomes or sequences of events, for example, flipping a coin or picking a marble from a bag. There are independent events, or events for which the outcome of one event does not change the likelihood of the other events. For example, flipping a coin and a number cube roll. Dependent events are events for which the outcome of one event changes the likelihood of the other events. For example, pick a marble from a bag, then pick a second marble without replacing the first marble. This would be dependent because what is available for the second pick depends very much on what the first marble picked was. And then sample space is a list of all possible outcomes for one or more events. And this, as an example, the sample space for flipping two coins is heads, 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 tails, tails, heads, and tails, tails. Events are independent events if the occurrence of one event does not affect the likelihood that the other events will occur. Events are dependent events if the occurrence of one event does affect the likelihood that the other event or events will occur. Now, likelihood, that's if it affects the probability, it affects its likelihood. Determine whether each set of events are independent or dependent and explain. Example 7.3.2. Numbers are picked from a hat containing numbered cards. You pick two numbered cards at the same time. The first card, you pick an even numbered card, and the second card, you pick a 13. All right, since you pick them at the same time, that's as if you pick one, keep it, and pick the next one, even though you're doing it at the same time. You can't get the same card twice. So the first card will not be available for the second card's pick. So depending on what you get the first time, it changes what's available the second time, making this dependent. The first card is no longer available for the second pick. And therefore, it's impossible to pick it for the second pick. You roll two number cubes. All right, picture rolling two number cubes. On this, it should be obvious that one number cube is not going to affect what comes up on the other number cube. So these are independent. Rather than saying the, let's say each. Each number cube has no effect on the other. Doesn't matter what you get on one, the other one's still going to have the same probabilities. You pick your favorite and second favorite ice cream from the frozen food section of a grocery store. Alright, so your favorite is butter pecan and your second favorite is burnt almond fudge. Alright, on this, if we're talking about favorite and second favorite, your favorite and second favorite cannot be the same. I mean, you can have a favorite and not have a second favorite, but then you'd only get one type of ice cream. So you'd probably have a second favorite. Anyway, they can't be the same one, so it is dependent because your favorite will be different than your favorite. Oh, than your second favorite. Okay, next example. Well, this isn't an example, this is more information. A sample space can be created using a table or tree diagram. Consider the compound event of flipping a coin and rolling a number cube. So in a table, you can see that the sample space are these 12 events listed here. And on the tree diagram, the sample space is created by following each of the branches all the way out and getting every option into the sample space. And there are 12 things in the sample space here. Okay, next, the fundamental counting principle, which we learned about earlier this week, can be used to determine the number of outcomes for compound events. You use the fundamental counting principle by multiplying the number of outcomes for each sub-event, so the individual events, together to get a combined number of outcomes for the compound event. Determine the number of possible outcomes for each compound event. Example 735. Rolling a number cube 3 times. Well, the first event would be rolling the number cube the first time, and there are 6 outcomes for that. The second event is rolling the number cube the second time, and there are 6 outcomes for that. Event number 3 has 6 options because the number cube still has the 6 there. This actually is independent, so that's why the probabilities don't get affected by the others. But there are 216 outcomes possible here. Okay, example 736. A sports jersey with a 2-digit number if each digit can be 0, 1, 2, 3, 4, or 5. We actually did this one earlier in the week. Event 1 would be the first digit and event 2 would be the second. The first digit has a total of 6 options. The second digit has a total of 6 options, giving us 36 different jersey numbers that we could have. Okay, next example. 2 members of a club are selected to be the president and vice president. There are 11 members of the club. So event 1 would be picking the president and event 2 the vice president. Now this actually is a dependent event. These are dependent events. For the president, any of the 11 members could be picked. But once the president has been picked, that person is no longer available to be picked as the vice president. So there are only 10 available for the vice president position, giving us a total of 110 different presidencies that could be formed in that club. Okay. Notice when using the fundamental counting principle on a dependent event such as this, you just figure out how many ways the event can occur, but you do it with the assumption that the previous event has already occurred. Okay, next example. You pick an outfit from 5 shirts, 4 pairs of pants, 3 pairs of shoes. You wear 1 shirt, 1 pair of pants, and 1 pair of shoes. So event 1 here is going to be the shirts, and there are 5 of them. Event 2 is going to be the pairs of pants, there are 4. And event 3 are going to be the pairs of shoes, there are 3 of those. This gives us a total of 60 outfits that can be worn with that combination of items. And those would be independent events. Okay, the probability of compound events. For independent events, the probabilities are multiplied together. Both probabilities are calculated as if they were single events and then multiplied together. So the probability of A and B happening is the probability of A happening, and then you just multiply by the probability of B happening. And if there's more than 2 events, you just keep multiplying those probabilities together. For dependent events, the probabilities have an effect on each other. The first probability can be calculated as if it were a single event, but the second and third, etc. events need calculated assuming the first event has already occurred. These probabilities can be multiplied together. Probability of A and B would be the probability of A multiplied by the probability of B, assuming A has already happened. And that we have to assume A has happened because in dependent events, the outcome of the first event does have an effect on the probabilities of the second event. Now, these actually, you can kind of treat them essentially as the same formula, because if it's independent, the probability of B happening after A, if A has no effect on B, then it's just the probability of B. Doesn't matter if A's happened or not. So they're essentially the same formula. You do the probability of A multiplied by the probability of B, assuming A has happened. And then you're going to multiply by the probability of C, assuming A and B have happened. And then you multiply by the probability of D, assuming A, B, and C have happened, etc. And you can do as many events as you want here. And again, if they are independent, it doesn't matter how A, B, or C has happened. In that case, you don't have to worry about how that changes the probability, because on independent events, they do not change the probability. So let's calculate some of these. 2 cards are picked from a deck of numbered cards with the numbers 1, 2, 3, 4, 5, 6, all the way up to 16. The card is returned to the deck, then another card is chosen. Determine the probability of each compound event. Now, I want you to kind of think in your head about these numbers. In fact, to make it easier for you to understand where I'm getting these from, let's say you're thinking about these numbers. Here they are. Those are the cards. They're numbered 1 through 16. Now, the first event is picking a 5. That has a 1 in 16 chance of happening. The second event is picking an even number. The even numbers include 2, 4, 6, 8, 10, 12, 14, and 16. There are a total of 8 of those. Okay, so we have a 1 in 16 chance for the first event and an 8 in 16 chance for the second event, giving us a total of an 8 in 256 chance of both events happening together. Now this does reduce nicely down to 1 out of 32. And one strategy you can use to make this easier to calculate is this 8 out of 16 can be reduced to 1/2. And then you just have 1 times 1 is 1, and 16 times 2 is 32. You can calculate it a little bit more easily that way. Okay, let's look at our next example. Probability of an even number and then a multiple of 3. Okay, we did even number here. There's 8 out of the 16 that are even. And then a multiple of 3, if I go through and circle these, 3, 6, 9, 12, and 15 are all the multiples of 3. And there are a total of 5 of them. So that's 5 out of 16. Now if we do a little bit of reducing first, that'll help us here. 8 sixteenths is the same as 1/2. 1/2 times 5 sixteenths, 1 times 5 on top, 2 times 16 on bottom. That is a probability of 5 out of 32 that you will roll pick an even number and then pick a multiple of 3. Okay, next example. We are going to pick a number less than 7. Less than 7, there are 6 out of the 16 numbers, because less than 7 will not include 7. And then greater than 7 would be the 8, the 9, 10, 11, 12, 13, 14, 15, and 16. There are 9 of them. So the second event has a 9 out of 16 chance of happening. Now, let's do some quick reducing here. 6 out of 16 is the same as 3 out of 8. So 3/8 times 9/16, multiplying straight across, 3 times 9 is 27. 8 times 16 is 128. And that won't reduce, so it's a 27 out of 128 chance, or probability, that you'll pick a number less than 7, followed by picking a number greater than 7. Next, the probability of picking 13, followed by picking 13. Now if you pick 13, there's only one 13 out of the 16. And for the second time, if you're going to pick 13 again, there's only one 13 out of the 16 options. This gives you a probability of 1 out of 256. Quite unlikely to occur. Okay, let's look what happens with dependent probabilities. 2 marbles are picked from a bag without replacement. There are 2 red, 3 blue, 4 green, 5 black, and 6 purple marbles in a bag. Determine the probability of each compound event. Now I'm going to do the little thought bubble thing like I did last time, so you can kind of see where the thought process is going here. Okay, there's our marbles. 2 reds, 3 blues, 4 greens, 5 blacks, and 6 purples. First, we're going to pick 2 black marbles. Now, these marbles are not being replaced. So, the probability of the first black marble, there's 1 of them. Actually, there's 5 black marbles out of a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Looks like there are 20 marbles total. Okay, so that's 5 out of 20 chance of picking black. Now that black marble is gone because we've picked it. It's dependent. Next, we're going to pick another black marble. And there are only 4 black marbles now. There are only 19 marbles left. So this is how dependent probability will work. You need to find the probability of the first thing happening and then make it happen. Have it actually occur, and then figure out the probability with that event already having happened. And then multiply these together. There's a little bit of reducing I can do here. 5 out of 20 is 1/4. And it looks like 4 on bottom and 4 on top can reduce. So this is just a probability of 1/19. There's a 1 in 19 chance of picking 2 black marbles. Okay, what's the probability of picking a red and then a green? So first we're going to pick a red. There are 2 reds out of the 20 marbles. Now we need to get rid of a red. And now we're going to pick a green. There are 4 green marbles out of the 19 marbles that are left because we got rid of one of the red marbles. This gives us a probability. Let's do a little bit of reducing. 2 out of 20 is 1 out of 10. Let's go ahead and multiply and then we'll reduce a little bit more. 1 times 4 is 4. 10 times 19 is 190. Let's go ahead and divide top and bottom by 2. And that should be 2 out of 95. There's a 2 out of 95 probability that you can pick a red and then pick a green. Okay, next. What's the probability of picking no purple marbles? All right, if you're going to pick no purple marbles, your first marble has to not be purple, and then your second marble has to not be purple. So let's start by picking not purple. 14 of these marbles are not purple out of the 20. Now, I'd have to get rid of one of the not purple marbles, and my second probability deals with not being purple, so it actually doesn't matter here, and it gets rather complicated if I had a problem that said picking not purple and then picking red, because if I got rid of the red in the first one, it would really mess things up. But that's beyond the scope of what we will learn in 7th grade. You will learn that in the future, but not at this time. So I'm just going to get rid of one of the marbles. It doesn't matter which one, so I'm not really going to mark off one of them at this time. But one of the marbles are gone. Okay? And then there's only 19 marbles left, and I'm going to pick not purple again. Well, there's still 6 purple marbles because I didn't pick it the first time. There are only 13 non-purple marbles now. So it's a 13 out of 19 chance the second time. Let's do a little bit of reducing here. This would be 7 out of 10. And 7 times 13 is 91. 10 times 19 is 190. And I do not believe that that will reduce. So your probability of picking no purple marbles in 2 picks is 91 out of 190. Okay, next, the probability of picking 2 red marbles. Okay, 2 red marbles. We're going to pick a red. Here it is. There's 2 marbles out of 20 that are red. Okay, now I've picked it. It's no longer there. And I'm going to pick another red marble. There's only 1 red marble left out of the 19 marbles that are there. So it's going to be 1 out of 19. Now 2 out of 20 we can reduce to 1/10. 1/10 times 1/19 is 1 out of 190. So the probability of picking both red marbles is 1 out of 190. Okay, let's look at, these are probabilities we calculated earlier in the week, but we're going to do it now with the compound probability formula we learned, rather than looking at sample spaces. So what's the probability that rolling 3 6-sided dice that you will end up with triples? All right, in the very first roll, I can get any number at all. It doesn't matter. So there's a 100% chance that I'm going to get a number. After I have gotten that, well, that's the probability of event 1. We can get any number there. Now, once we've gotten that number, the second event, I have to get the same number, and the third event, I have to get the same number. Now, this, it can be any number, but there's only one number available here and one number available here. So it's going to be 1 out of 6 and 1 out of 6 for the remaining numbers. So this gives us 6 out of 216 when we multiply all those together, which reduces to 1 out of 36. Next, find the probability of 2 heads and green on the spinner. All right, so let's treat these as event 1, event 2, and event 3. And we're going to do the probabilities multiplied together here. We'll make event 1, event 2, and event 3 here. Event 1, getting heads on the quarter, is 1/2. Event 2, getting heads on the dime, is also 1/2. And event 3, getting green on the spinner, is 1 out of 4. This gives us an overall probability of 1 out of 16. Okay, let's look at just a few more here real quick. You roll a number cube twice, find the probability of the events. Rolling a 3 twice. Okay, rolling a 3 the first time, 1 out of 6. Rolling a 3 the second time, 1 out of 6. These are independent events. You get an overall probability of 1/36. Rolling an even number and a 5. There are 3 out of 6 even numbers for the first event, 1 out of 6 for the second event. Now, a very common mistake students make is to treat that number 5 as the number of outcomes, but there's only one 5, there's only one outcome. Anyway, multiplying across carries 3 out of 36, which is 1/12 being the probability. Okay, next, rolling an odd number and a 2 or a 4. For the first event, an odd number happens 3 out of 6 times. A 2 or a 4, that's 2 events out of 6. This is a probability of 6/36 or 1/6. There is a 1/6 probability of rolling an odd number and then rolling a 2 or a 4. Number 4, rolling a number less than 6 and then rolling a 3 or a 1. A number less than 6, there are 5 numbers less than 6. The only one that's not less than 6 is 6 itself. And the second event has 2 options out of 6 because it's a 3 or a 1. This gives us a probability of 10 out of 36, which is 5 out of 18. So you have a 5/18 probability of rolling a number less than 6 followed by rolling a 1 or a 3. You randomly choose a letter from a hat with the letters A through J. Without replacing the first letter, you choose a second letter. Find the probability of the events. So the letters A through J, I'm going to go ahead and write down here. A, B, C, D, E, F, G, H, I, J. Okay, that's it. Oh, I see what I did there. H, I, J, K, that's it. Very clever, Mr. Goodrich. All right, let's see. Let's group those together. And we'll go ahead and lock them in place so that I can erase over top of them as needed. Okay, choosing an H and then choosing a D. I'm going to choose the H, and now it's gone. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 options. 1 out of the 10 options are H. And then I'm going to choose a D. Well, the H is no longer available, so there's only 9 options now. And if I pick the D, there's only one of those. So the probability of picking an H and then picking a D is 1 out of 90. Okay, next one. Choosing a consonant and then an E or an I. Consonants include B, C, D, F, G, H, and J. That would be 1, 2, 3, 4, 5, 6, 7. 7 out of 10. Now I picked a consonant. It doesn't really matter which one because the next pick is going to be a vowel and it will not overlap. So let's just get rid of one of them. And then for the next one, see that we're actually not getting rid of one of them. This is just going on in the mind so that we kind of can picture what's going on. It wouldn't matter which one I got rid of. And for the second one, there's only 2 that are E or I. And that's out of the 9 that are left. This gives us a probability of 14 out of 90, which is 7 out of 45. So there's a 7 out of 45 chance or probability of picking a consonant followed by picking an E or an I. Okay, next, choosing a vowel and then choosing an F. I got to make sure that says F. Yes, it does. Okay, so choosing a vowel first. There's 1, 2, 3 vowels out of 10. One of the vowels is now gone. Then choosing an F, there's only 1 F out of the 9 remaining letters. This gives us a probability of 1 out of 30. It'd be 3 out of 90, which reduces to 1 out of 30. Okay, next, choosing a vowel and then choosing a consonant. The vowels, of course, there's A, E, and I. That's 3 out of the 10. We get rid of one of the vowels. Then for the consonant, there's only 9 letters left. And 1, 2, 3, 4, 5, 6, 7 of them are consonants. This gives us a probability of 21 out of 90. If we divide top and bottom by 3, we get 7 out of 30. The probability of picking a vowel and then a consonant is 7 out of 30. Okay, you have 3 clasp bracelets, 4 watches, and 5 stretch bracelets. You randomly choose 2 from your jewelry box. What's the probability you will choose 2 watches? So we have 3 clasps, 4 watches, and 5 stretch bracelets. Just abbreviating them here. So doing this mental thing again. Oh, looking a little down there. Let me change it there. Let's make him really happy. Got to be happy. He's doing math right now. Okay. So you're going to get the probability of choosing 2 watches. So the first event, we're going to have to pick a watch. Now, we are picking 2 at the same time, so it's not going to be replaced. So the watch, let's see, there are 3 and 4 make 7 and 5 make 12. There are 4 out of 12 that are watches. Now that I've picked one, there's only 3 out of 11 that are watches for the second event. This gives us a total of 12 out of 132, which reduces to 1 out of 11. There's a 1 in 11 probability of choosing 2 watches at random. Who wears 2 watches anyway? Oh wait, I do. Okay, just a few more examples. You flip a coin and then roll a number cube twice. What's the probability of each event? Okay, flipping a coin and rolling a number cube, these are independent, so we don't have to worry about changing the probabilities here. Flipping heads is a 1 and 2. Rolling a 5 is a 1 and 6. And rolling a 2 is a 1 and 6. This is a 1 in 72 probability. Number 11, we're going to flip tails, which is a 1 in 2 chance, 1 in 2 probability. An odd number happens 3 out of 6, and a 4 happens 1 out of 6. This is a probability of 1/2 times 1/2 times 1/6. That's 1/24th probability. Okay, flipping tails, which happens 1/2 of the time. Rolling a 6 or a 1. That's 2 options out of 6. And rolling a 3, that's 1 option out of 6. This gives us a probability of 1/2 times 1/3 times 1/6. And that would be, let's see, 1/36th is the probability of that happening. Okay, flipping heads is a 1 in 2 chance. Not rolling a 2, there are 5 numbers out of the 6 that are not 2. And rolling an even number, there are 3 out of 6 that are even. 1 times 5 times 3, that's 15. 2 times 6 times 6 is 72. Divide top and bottom by 3, and we get 5 out of 24. So 5/24 is the probability of flipping heads, not rolling a 2, and then rolling an even number. 2 cards are picked from a deck of cards that are numbered 1 through 20. What's the probability of picking a 7 and then picking a 10? All right, we got to think about this. Is this independent or dependent? 2 cards are picked. It doesn't say anything about it being replaced. They're probably picked at the same time, so we need to treat these as dependent events. So for the first pick, there are 20 cards available. For the second pick, there are 19 cards available. Okay, how many 7s are there? There's only one 7 in the whole deck. How many 10s are there? There's only one out of the 19 cards remaining. This is a probability of 1 out of 380. So it's not very likely to happen. Okay, in your assignment, on number 1, you're just calculating some probabilities. Just find the probability of each event and then multiply them together. Same with number 2. The difference here is in number 2, you're not replacing. So these are going to be dependent probabilities. Number 3, classifying a triangle. Okay, so that's a review problem about triangles. What type of triangle has those 3 angles? That would include whether it is acute, right, or obtuse, and whether it is scalene, isosceles, or equilateral. Number 4, use the fundamental counting principle to find how many unique answer responses there are. Okay, there are 8 different events here, and there are a certain number of ways each event can occur. Number 5, we've got 5 events. Order the events from least to most likely, most unlikely to most likely. So most unlikely will have the smallest probabilities, and most likely will have the highest probabilities. Number 6, this is a scale model problem of the Statue of Liberty. Number 7, this one is an interesting one. It looks like there's only 2 events, but there are actually 4 events going on here in each of those. Number 8, just more probability, dealing with a spinner, a coin flip, and then doing the spinner again. And that's what to expect on that. Thank you for watching.